In this chem activity 101, we are going to be looking at alpha amino acids and small peptides. Alpha amino acids are like the structures shown, in which we have a carboxylic acid. Next to that, in the alpha position, we have an R group of some type and an amino group. The R group ranges from a hydrogen for glycine up to rather fancy structures with rings or chains and other functional groups. One specific example of an alpha amino acid is L-alanine, in which the R group is a methyl group. The naturally occurring amino acids are by and large L configuration, meaning they have the shape shown, with the R group wedged back, hydrogen forward, carboxylic acid to the right, nitrogen to the left. This would be an S configuration when you have 1 to 2 to 3 standing behind the board, or reversed because the lowest priority group is coming towards you, you'd end up with counterclockwise. Most, but not all, alpha amino acids are of an S configuration, but all of the L amino acids have the shape shown. The L is related to the three-dimensional shape, but does not necessarily correlate to the direction that plane polarized light is switched. If you remember, L was originally a word for lev rotatory or minus direction of optical rotation. In the case of alpha amino acids, the L configuration comes from another compound which does experimentally rotate light in the lev rotatory direction. This alternative compound, glyceraldehyde, is the simplest of our sugars and is the basis for the nomenclature of sugars as D or L, as well as the amino acids as D and L. You can see that the corresponding importances of the side groups correlate between glyceraldehyde and carboxylic acid, where the aldehyde group is equivalent to the carboxylic acid group, the amino group is equivalent to the OH, the hydrogens match, and the CH2OH replaces the R group. Now these amino acids are drawn in a form that would occur in organic solvents. However, in neutral water, you're going to see a different ionic form of amino acids. So let's write that for the alanine structure shown. If you imagine alanine fully protonated, it actually has two acidic protons. It has an acidic proton on the amino group and acidic proton on the OH. We have pKa's available from tables for those two groups. The amino group has a pK of 9.87, and the carboxylic acid group has a pK of 2.35. This shouldn't be surprising. Most amino groups are pKa's somewhere near 10, and most carboxylic acids are somewhat under 5. In highly acidic solution, both of these positions will be protonated. However, at physiological pH, only the amino group is protonated. So if we say pH equals 7, we have one proton taken off and one proton still there. It might not surprise you that it's the most acidic proton, the carboxylic acid 2.35, that's taken off. The less acidic proton remains on. This actually illustrates the Henderson-Hasselbalch equation, that the difference between pH and pKa is equal to a logarithm of the concentration of base in solution divided by the concentration of acid in solution. What this tells us is that we can actually predict what the base acid concentration for any acidic site is, the ratio, at any pH if we know the pKa's. Ultimately, what this equation tells us is that if the pH of solution is greater than the pKa of that position will be deprotonated at that pH. So at pH 7, which is greater than the pKa of the OH group, this position is deprotonated. On the other hand, the pH of the NH3 position is 9.87, so at pH 7, this position is still largely protonated. You will get to work with this equation in the chem activity as well. Finally, the chem activity takes a look at peptide bonds. And peptide bonds are formed by joining a series of amino acids together, normally written in the N to C configuration. This process occurs in the process of or translation of RNA to proteins. It occurs by nucleophilic acyl substitution, and it occurs with the loss of one molecule of water. Although it does not directly involve the amino group adding to the carboxylic acid, there's an intermediate step in which the carboxylic acid is attached to a template. It is indeed a nucleophilic acyl substitution, where the amine of one amino acid combines with the carboxylic acid of a neighboring amino acid to make a new amide bond. In the process, we lose a net equivalent of water for each bond formed. The resulting tripeptide would now have two new amide bonds between the carbon and nitrogen of what used to be two separate amino acids. And this tripeptide is again normally written from the N to C end, nitrogen on the left, carboxylic acid on the right, and once again, if we were in neutral solution at physiological pH, we'd expect carboxylic acids with pKa's less than 5 to be deprotonated, and we would expect the amine terminal end with a pKa of close to 10 to be in the protonated form. Thus, alpha amino acids with their chirality centers, their different R groups, their definite configuration of S, and their propensity for losing protons in solution based on the pH of the solution. These amino acids will combine together to make peptides, which combine to make longer chains, proteins, form enzymes and structural features.